Have you ever found yourself wishing you could just know the best way to do something, not just in this moment, but always? Imagine if a computer could learn to navigate a complex maze, master a game like backgammon, or even perfectly manage something intricate like an elevator system, all by itself, through sheer trial and error, getting smarter with every single attempt.
It's a powerful vision, isn't it? The ability for an agent to truly adapt and optimize its behavior purely from interacting with the world,
Right.
rather than needing explicit instructions for every single scenario it might encounter. That's the core challenge we're exploring today.
Absolutely. And it's a concept that truly reshapes our understanding of intelligence. Today, we're embarking on a deep dive into some of the most fascinating and powerful learning methods at the very heart of artificial intelligence. Specifically, we're going to untangle the brilliant ideas behind reinforcement learning and then zero in on temporal difference learning. We'll explore its incredibly effective variations, SARSA, Q-learning, and the elegant concept of n-step bootstrapping, which culminates in the truly insightful idea of eligibility traces.
Our mission for you in this deep dive is to make these concepts crystal clear. Even if you're completely new to the world of AI, we'll guide you step by step.
Yeah, we'll cut through any jargon to give you the essential nuggets of knowledge.
We'll explore how these intelligent agents learn from experience, not by being told what to do, but by discovering which actions maximize a special reward signal over time.
And why does this matter to you? Because understanding these core principles of how intelligent systems learn is a powerful aha moment.
Definitely.
It's about more than just algorithms. It's about a fundamental way of thinking about how learning and decision-making happen in dynamic, uncertain environments, giving you a shortcut to truly understanding one of the most exciting fields in technology. So let's get started. To properly appreciate temporal difference learning, we first need to lay a solid foundation. So let's begin with the big picture. What exactly is reinforcement learning?
At its core, reinforcement learning, or RL, is this fascinating paradigm that's actually three things at once. It's a type of problem, a class of solution methods for that problem, and an entire field of study.
Okay.
Fundamentally, it's all about how an intelligent agent learns to map situations, what we call states, to actions with the ultimate goal of maximizing a numerical reward signal.
Right. Kind of like training a dog.
Exactly like training a dog. You don't explicitly tell it how to sit perfectly, but you give it a treat or reward when it performs the action you want. Over time, it learns the optimal actions to get the most treats.
So it's not just about getting one treat, but consistently getting rewards over the long haul. What makes this approach distinct from other kinds of machine learning that people might be familiar with?
That's a crucial question. RL has a few key distinguishing characteristics. First, it's a closed-loop problem.
Closed loop.
Yeah. What this means is that the agent's actions don't just happen in isolation. They directly influence its future inputs and the situations it encounters. The agent is actively participating and changing its environment.
Okay. Imagine driving a car.
Yeah.
Every turn you make doesn't just move you forward. It changes your perspective, the traffic patterns, and the road conditions you'll face next. Your choices directly shape your future experience.
That's a fantastic analogy. It's not like just passively analyzing a data set. The agent is creating its own data as it goes.
Exactly. Second, and this is truly fundamental, there are no direct instructions.
No instructions.
None. Unlike many other forms of machine learning where you feed an algorithm labeled example saying, this is a cat or this is the correct answer, an RL agent isn't told what action to take in a given situation. It must discover the best actions by trying them out and observing the results. This is pure trial and error learning.
Okay.
And third, there are often delayed consequences. An action doesn't just affect the reward you get immediately. It can profoundly shape future situations and all subsequent rewards, sometimes many steps down the line.
This introduces what's known as the credit assignment problem. How do you know which specific action, perhaps taken much earlier, was responsible for a really good or bad outcome you're experiencing now? It's like a butterfly flapping its wings and causing a storm later, you know?
The credit assignment problem. That sounds incredibly tricky to untangle.
Yeah.
So how does this ongoing interaction between the agent and its world actually happen in an RL system?
This is where we define the agent-environment interface. You have the agent, which is the learner and decision maker, the brain, if you will.
Okay.
And then you have the environment, which is everything outside the agent that it interacts with. At each discrete time step, a continuous cycle of interaction takes place.
A cycle.
Yeah. First, the agent receives a state from the environment, its current perception of the situation. Second, based on that state, the agent selects an action.
Makes sense.
Third, one time step later, the environment transitions to a new state, 7 plus Venable, and sends a numerical reward, Masterful, back to the agent.
So it's a constant loop. Perceive the state, decide on an action, execute, see the new state, receive a reward, and repeat. It's like a mini experiment happening every single moment. Can you give us a really tangible example of this cycle?
Of course. Let's think about a baby gazelle learning to run just minutes after being born. Its wobbly first steps are its actions.
Right.
Its current balance and position, whether it's upright or starting to tip, are its state. If it falls, that's a negative outcome, a kind of negative reward, and it lands in a new state on the ground.
Yeah.
If it manages to stay upright, that's an implicit positive reward, leading to a new state where it's still standing or even moving forward. Through this incredibly rapid trial and error, it learns to refine its motor control to maximize staying upright and eventually running.
Wow.
Or imagine someone like Phil trying to make breakfast. Each step, an action like opening the fridge, changes the state of his kitchen and the breakfast-making process. Getting the milk out is progress, a small positive reward, and changes his state to milk is out. This constant cycle of action, state change, and reward guides his overall goal.
That's very clear. The goal isn't just about one specific moment, but about achieving the best possible outcome over a continuous sequence of decisions.
Exactly. That reward signal from the environment is the single crucial piece that defines the agent's objective. The agent's sole goal is to maximize the total reward it receives over the long run, not just immediate rewards.
Right.
This leads us to a foundational idea called the reward hypothesis. It suggests that all goals and purposes, no matter how complex, can be formalized as maximizing the expected cumulative sum of this scalar reward signal. It boils down to defining what you want to achieve, not how you should achieve it.
So we just need to set the scoring system correctly, and the agent will figure out the game. But that also means if we design the reward function poorly, the agent might find a clever, unintended way to get a high score without actually achieving what we wanted, right?
You've hit on a common challenge. Crafting effective reward functions is an art in itself. It really is. Now, to measure this total reward we're trying to maximize, we use the term return, which is simply the cumulative reward.
Return. Okay.
We calculate it differently for different kinds of tasks. For episodic tasks, which have a natural end, like a game of chess, a robot completing a specific maze, or a single attempt to balance a pole, the return is straightforward.
Yeah.
It's just the sum of all future rewards until the final time step. So if you're in a state at time t's, your return is RT plus 2 plus dots plus RT.
Simple enough. For a game, you just add up all the points from that moment until the game is over.
But what about tasks that don't end? For continuing tasks like process control in a factory, keeping a robot balanced indefinitely, or a long-lived robot patrolling an area, interaction goes on indefinitely.
Right. That seems tricky.
Here, simply summing infinite rewards would lead to infinite values, which isn't mathematically useful. So we introduce a concept called discounting.
The discount rate. I've heard of this in economics and finance, where future money is valued less than money today. Is it similar?
Very similar. We use a discount rate, which is a value between 0 and 1. Future rewards are multiplied by gamma for each step into the future.
Okay.
So a reward 1 step away is multiplied by gamma, 2 steps away by gamma 2, 3 steps away by gamma 2, and so on. This effectively means immediate rewards are valued more than distant future rewards.
Makes sense.
The return then becomes RT plus 1 plus gamma plus 2 plus gamma 2 plus 3 plus dots. If gamma's $1, the agent only cares about the immediate reward, making it very short-sighted.
Very impulsive.
Exactly. If gamma is closer to 1, say R99, it becomes more far-sighted, valuing future rewards almost as much as immediate ones. This discounting also has the useful property of guaranteeing that the sum converges to a finite value, even for tasks that go on forever.
So a high gamma means a far-sighted agent planning for the distant future, while a low gamma makes it focused on immediate gratification. That's a powerful dial to control an agent's behavior.
It absolutely is. And for mathematical elegance and simplicity, we can actually use a unified notation by viewing episodic tasks as a special kind of continuing task.
Oh, how does that work?
We imagine that once an episodic task ends, the agent simply enters a special absorbing state where it receives only 0 rewards from then on. This neat trick allows us to use a single mathematical notation for both types of problems.
Clever. So the math handles both finished games and ongoing processes the same way.
Pretty much, yeah.
So we have rewards, and we know how to calculate the cumulative return.
Hmm.
But how does an agent actually know which actions are good in the long run?
Yeah.
How does it estimate that elusive goodness before it's actually finished the task?
That's precisely where value functions become indispensable. Almost all reinforcement learning algorithms rely on estimating these functions.
Okay.
Value functions tell us how good it is to be in a particular state, or to perform a particular action in a given state, in terms of the expected future reward, the expected return. It's essentially a prediction of the total future reward you can anticipate from that point onward.
So like a running score predictor.
Yeah.
If I'm in this specific situation in a game, a value function would tell me how many points I can expect to get from here to the end.
Exactly that. And there are two main types. The state value function gives you the expected return if you start in-state SIZs and then follow a specific policy.
And a policy is just the agent's strategy, right? Like what it does in each situation.
Exactly. It dictates what action the agent chooses in each state. The other type is the action value function. This tells you the expected return if you start in-state Zellers, take a specific action, and then follow policy says thereafter. The action value function is often more directly useful for control problems because it allows the agent to directly compare the goodness of different actions it could take from a given state.
So VB tells me how good a state is overall if I stick to my current plan, whereas UBA day tells me how good it is specifically to take action A from state as and then stick to my plan. That seems like the real decision-making engine.
You've got it. That's exactly right. Ultimately, our goal in reinforcement learning is to find the optimal value functions denoted Vivace and Gallers.
Optimal, meaning the best possible.
The best possible. These represent the maximum possible value achievable from any state or state action pair, respectively, under what we call an optimal policy. An optimal policy is, quite simply, a policy that is better than or equal to all other policies. Finding these optimal value functions and the corresponding optimal policy is usually the ultimate aim of the entire learning process.
Got it. So find the best possible value and the strategy that achieves it.
That's the game. Hashtag tag 1.4, the exploration-exploitation dilemma.
We've now got the rewards, the return, and value functions to estimate goodness. But this all assumes the agent already knows what's good and bad. How does the agent actually discover those optimal actions and their values when it starts from scratch? It can't possibly know them in advance.
You've stumbled upon a core challenge unique to reinforcement learning, the exploration-exploitation dilemma.
Yes. Heard of this one.
This is where things get truly interesting. On one hand, the agent wants to exploit what it already knows. This means choosing actions that it has tried in the past and that have yielded high rewards. It maximizes the immediate known reward.
Makes sense. Stick with what works.
Think about it. If you're in a row of slot machines and you know one particular lever has paid out consistently in the past, you'd be inclined to keep pulling that lever. That's exploitation.
That's the sensible, logical thing to do.
But on the other hand, the agent also needs to explore. This means trying new actions that it hasn't selected before or hasn't selected often enough to have a reliable estimate of their value. Exploration is vital because it allows the agent to discover potentially even better actions in the future, which could lead to significantly higher long-term rewards.
Right.
What if there's another slot machine lever right next to your favorite that pays out 95% of the time, but you've never tried it? If you only exploit, you'd never discover it.
So you can't just exploit because you might miss out on something amazing. And you can't just explore because you'd be wasting valuable time on potentially bad actions. It's a classic balancing act.
It is, and you can't perfectly do both with a single action. Overexploiting means you might miss out on genuinely better options, while overexploring means you might spend too much time on suboptimal actions, incurring unnecessary costs or lower rewards. It's a constant trade-off.
So how do we handle it?
Well, one of the most common and effective strategies to balance this is called epsilon greedy action selection. Epsilon greedy.
How does that balance work in practice?
It's surprisingly simple and elegant. Most of the time, with a probability of $1 epsilon, where epsilon is a small number like 0.1, 0.01, or even smaller, the agent chooses the greedy action.
That's one it knows so far.
Exactly, the one with the highest estimated action value. But occasionally, with a small probability of epsilon, it chooses a random action from all possible actions, even if it thinks that action isn't the best right now.
Oh yeah.
This simple mechanism guarantees that some exploration always happens.
So if epsilon is $1 cents, The agent will pick the best known action 90% of the time, but then randomly try something new 10% of the time.
Precisely. To illustrate, imagine an n-armed bandit problem, like having 10 different slot machine levers. A purely greedy approach might quickly get stuck on a suboptimal lever if its initial few pulls yielded good results, simply never trying the others enough.
Right, it gets stuck in a local optimum.
Exactly. But an epsilon greedy approach, even with a tiny epsilon, will eventually try all the levers and discover their true reward potential. Our source material highlights that an epsilon 0.0111 method might initially learn slower than an epsilon 0.11 method because it explores less aggressively,
Makes sense.
but it can often achieve higher long-term rewards because it wastes less time on exploration after it has found good actions. It settles into exploiting the best options more reliably.
So a little bit of disciplined exploration consistently pays dividends over time.
Absolutely. And this dilemma becomes even more critical in environments where the optimal actions might change over time, a concept known as non-stationarity,
Like the rules of the game change.
or just the environment's dynamics shift. In such dynamic cases, continuous exploration isn't just a nicety, it's essential for the agent to adapt to the changing environment, rather than stubbornly relying on what worked in the past. Even if the environment itself is stationary, the learning process itself creates a kind of non-stationarity,
Oh, interesting.
because the agent's estimated values of actions are constantly changing. What was greedy yesterday might not be the best estimate today, reinforcing the need for continuous exploration to refine those estimates.
That's a really subtle but important point. The learning itself changes the landscape.
It does.
We've now established the core principles of reinforcement learning, how agents interact, what their ultimate goal is, and the fundamental challenge of balancing exploration and exploitation. Before we unveil the central topic of our deep dive, temporal difference learning, it's incredibly helpful to understand two foundational approaches that TD learning draws from and, in many ways, intelligently combines. Let's start with Monte Carlo methods.
Monte Carlo methods are a fantastic place to begin because they're quite intuitive. The key idea is that these methods learn value functions directly from raw experience, meaning they don't need a formal model of the environment's dynamics.
No model needed.
Nope. They essentially learn by simply averaging the returns observed from complete episodes.
So they don't need to know the physics of how the world works,
Yeah,
just how it responds when they try something.
exactly. Here's how it works. To estimate, say, the value of being in a particular state sin while following a policy T way, the agent follows that policy for an entire episode from start to finish.
The whole thing.
The whole thing. Once the episode ends, the actual total return from each state or state action pair visited during that episode is known. The estimate for that state or pair is then updated by averaging all the returns observed after it was visited across many, many episodes.
And are there different ways they might average these returns?
There are a couple of classic variants: first visit Monte Carlo and every visit Monte Carlo. First visit MC averages returns only after the first time a state is visited within an episode.
Okay.
Every visit MC, as the name suggests, averages returns after every time a state is visited within an episode. While their theoretical convergence properties differ slightly, the core principle of learning from complete episodes using observed returns remains the same. For a beginner, the important distinction is simply that they wait for the full outcome.
What would you say are the biggest advantages of this approach?
The main advantages are compelling. First, they are entirely model-free. You don't need to understand the complex inner workings or rules of the environment. You just interact and observe.
That seems huge.
It is. Second, they're conceptually simple to grasp. And third, they can efficiently focus on subsets of the state space, meaning you can accurately evaluate a small, important region of interest without needing to compute values for the entire, potentially enormous, state space.
That sounds pretty powerful. But what are the limitations?
The primary limitation is that Monte Carlo methods require waiting until the end of an episode to make any updates. You only know the true return once the entire sequence of events has played out.
The patience factor.
Exactly. This can be very slow for tasks with long episodes, and it's problematic for continuing tasks that don't have natural terminations at all. Imagine a robot that's supposed to operate continuously for years. You can't wait for an episode to end to teach it something.
Okay, so Monte Carlo is experience-based and patient, but that patience can be a drawback. What about the other foundational approach? Dynamic programming.
Dynamic programming, or DP, is almost the inverse in some crucial ways. DP methods can compute optimal policies and value functions, but they come with a very demanding requirement. They need a complete and accurate model of the environment's dynamics.
A model, so they need to know the rules of the world.
Yes, exactly. And crucially, and this is where it foreshadows TD learning, DP methods update estimates based on other learned estimates, a process we call bootstrapping.
Okay, bootstrapping. So DP is model dependent, and it refines its predictions using its own existing predictions, not necessarily actual experiences from the world.
Precisely. DP algorithms are built upon fundamental mathematical relationships called the Bellman equations. These equations describe the self-consistent relationships between the value of a state and the values of its successor states. They essentially state that the optimal value of a state must equal the expected return for the best action from that state, considering all possible outcomes.
How does it actually work in practice to use these equations?
DP algorithms involve iterative sweeps through the entire state space. In each sweep, they update the value estimates of states, or state action pairs, using these Bellman equations.
Okay.
For example, in a process called policy evaluation, the value of a state SEPA is updated based on the expected immediate reward, crus 1 $, plus the discounted value of the next state, AMAPI plus 1. This is the essence of bootstrapping. You're updating an estimate using other estimated values.
Aye.
Instead of waiting for the actual final return, like Monte Carlo, DP uses its current estimate of what the next state's value will be.
So it's constantly refining its estimates by looking at its neighbors' current estimates, rather than waiting for the final truth. What are the big benefits of this powerful approach?
The main advantage is that with a perfect model, DP methods are guaranteed to converge to optimal policies. They also provide an incredibly powerful and rigorous theoretical framework that underpins much of reinforcement learning.
But I'm guessing that complete and accurate model requirement is a pretty big hurdle for many complex real-world problems.
It's the primary limitation, and it's a huge one. Such a model is often unavailable or far too complex and massive to store or compute in real-world scenarios.
I'll eat that elevator example.
Exactly. Consider an elevator dispatching problem with just 4 elevators serving 10 floors. Our sources indicate this system can have over 10 unique states. If you tried to calculate the optimal policy for that with DP, even if you could update one state per microsecond, it would take over 1,000 years just to complete one sweep through the state space.
Wow. 1,000 years.
Yeah.
Yeah.
This exponential growth in computational requirements with the number of states is famously known as the curse of dimensionality. Additionally, DP typically uses full backups, meaning it considers the complete distribution of all possible next states and their probabilities, which can be extremely computationally intensive for large problems.
So Monte Carlo is experience-based and patient but slow, while dynamic programming is model-based and can be optimal, but quickly becomes computationally impossible for large problems.
Yeah.
It really sounds like we need something that can get the best of both worlds.
Precisely the motivation for TD learning.
And this brings us to the star of our deep dive, temporal difference learning, or TD learning. This really sounds like the elegant solution that bridges the gap we just identified.
It absolutely is. If one had to identify one idea as the most central and genuinely novel contribution to reinforcement learning, it would undoubtedly be temporal difference learning. It brilliantly combines the best aspects of Monte Carlo and dynamic programming.
How does it manage to blend those two approaches, which seemed almost opposite in their requirements?
Well, the magic is in this. Like Monte Carlo, TD methods can learn directly from raw experience, from interacting with the environment without needing a formal model of the environment's dynamics. You just observe what happens.
Okay, model-free, check.
But then, like dynamic programming, TD methods update estimates based in part on other learned estimates. They bootstrap without waiting for a final outcome or the end of an episode.
So it's model-free and it bootstraps. That sounds incredibly powerful. What's the core operational difference that makes it so unique compared to Monte Carlo?
The key game-changing difference from Monte Carlo is that TD methods make updates after every single time step rather than waiting until the end of an entire episode.
Every single step.
Every step. This means they can learn continuously, making progress even in tasks with extremely long episodes or in never-ending continuing tasks.
That's a huge advantage. You don't have to finish the entire game or task to start learning something valuable. Tell us about the simplest form of this PD0.
PD0 is the most basic and fundamental temporal difference method. Its update rule for the value of a state, CSD, is beautifully simple. VSE plus alpha RT plus 1 plus gamma VST plus 1.
Let's unpack that formula a bit, because for someone new to this, those symbols can look daunting. What does each part mean in plain language?
Let's break it down. The entire bracketed term, tree EP plus 1 plus gamma V ST plus 1, is called the TD error, or delta lies. It's essentially the surprise, the difference between what we expected and what we got.
This is a surprise, okay.
So, del T plus 1 is our old current estimate of the value of the state city we are in right now.
Our prediction.
Right. Drel T plus 1R is the actual reward we just received after taking an action and moving to the next state. This is real, observed data.
Got it.
Gamma via T plus 1 is the discounted estimated value of the next state, Zal's T plus $1. This is the bootstrapping part. We're using our current best guess of the future value, Val's T plus 1, rather than waiting for the true unknown value.
Using an estimate to update an estimate.
Exactly. So the expression gel T plus 1 plus gamma ST plus 1 is called the TD target. It's our new improved estimate for the value of the current state, formed by combining one step of real experience, gel T plus 1 and R, with our bootstrapped estimate of the future.
Okay, the target.
And the parameter alpha is our step size, or learning rate, and it controls how much we adjust our old estimate based on this TD error. A small nudge.
So the TD error is basically how much our old prediction for a state's value differs from this new one-step-ahead prediction we just observed.
Yeah.
And we use that error to tweak our old estimate, constantly refining our understanding.
Exactly. We call these sample backups because, like Monte Carlo, they look ahead to a single sample successor state and reward, unlike DP methods, which consider a complete distribution of all possible successors.
This sounds like a subtle but profound difference. Can you give us a really clear, relatable example to show how this immediate updating in TDD works compared to Monte Carlo?
Let's revisit our driving home analogy. Imagine you leave the office and predict it will take 30 minutes to get home.
Okay.
5 minutes into your drive, it suddenly starts raining heavily, and you immediately re-estimate it will now take 35 minutes from your current position. So your new total predicted time from when you started would be 5 minutes elapsed, plus 35 minutes remaining, 40 minutes. A Monte Carlo method would wait until you're actually home to update your initial 30-minute estimate. It would only learn from the actual total time it took, say, 42 minutes.
Only learns at the end.
Right. TD0, however, would immediately update your initial 30-minute estimate at that 5-minute mark. It would use the observed reward, the 5 minutes elapsed, and your new estimate for the remaining journey, 35 minutes, to correct its initial 30-minute prediction.
It learns right away from the rain.
Exactly. This means learning starts much, much sooner. You don't have to finish the entire journey to realize your initial estimate was off and begin improving it.
That's incredibly powerful. You're constantly course-correcting based on fresh information, even if that information is still partly an estimate of the future. It's like having a navigation system that updates its ETA every second.
That's a great way to put it.
This ability to update immediately is a truly revolutionary aspect of TD learning, especially when we move from just predicting values to actually controlling the agent, that is, getting it to learn what actions to take.
Yes, this is where it gets really practical. We typically accomplish this within the framework of generalized policy iteration, GPI.
The continuous interplay between improving our value estimates and then improving our actions based on those estimates.
Precisely. GPI involves two continuous processes. Policy evaluation, where you improve the estimate of the value function for your current policy, and policy improvement, where you improve the policy itself, meaning your action choices, based on that updated value function. It's a loop.
Evaluate, improve, evaluate, improve.
Exactly. Now let's look at how TD methods implement this control, starting with SARSA.
Okay, SARSA. That's quite an acronym. What does it stand for, and how does it help an agent learn actions?
SARSA stands for State, Action, Reward, State, Action.
SARSA.
Got it. The name itself tells you exactly what sequence of information is used in its update. It's an on-policy TD control algorithm. Its update rule for the action value function, QSDO, which, remember, tells us how good it is to take action and states off variables at Q soft arrow plus alpha all plus 1 plus gamma, Q plus 1 at star plus 1.
So it looks very similar to the TD0 update rule we just discussed, but now it's specifically updating the value of a state-action pair. And the critical part is that it's using the value of the next action actually taken, ante plus 1 a dual, in the next state, Searsalt, to form its target. That's the A in SARSA.
Exactly, because SARSA learns the action value function for the exact policy it is currently following, including any exploratory actions it might take. We call it on policy.
Yeah, on policy. Learning based on what it actually does.
Correct. If your agent is using, say, an epsilon greedy policy to explore, SARSA learns the value of that specific epsilon greedy policy. It essentially learns the value of the path it actually takes, errors and all.
That's a key distinction. Can you give us an example of how this on-policy nature plays out in a practical scenario?
A classic example from our sources is the windy grid world. Imagine a grid maze where you need to move from a start point S to a goal G. However, some squares have an upward wind that pushes you one square up, regardless of your intended movement.
Okay, tricky.
Crucially, there's also a cliff nearby that gives a large negative reward if you fall off it.
Ouch.
An on-policy method like SARSA, using an epsilon greedy policy, will account for its own exploration. If an exploratory action, perhaps combined with the wind, causes it to get pushed toward the cliff and experience a negative reward, that negative experience immediately gets factored into its Shulata values for the actions that led to that near fall.
So it learns from those oops moments.
It does. What this means is that SARSA will tend to learn a path that avoids the very edge of the cliff or the most turbulent windy squares, even if that path is slightly longer. It learns a safer path that accounts for the potential negative consequences of its own exploratory actions. It builds a buffer of caution into its learned policy.
So it learns to be cautious because its own random moves could get it into trouble, and it wants to avoid that. That makes perfect sense for an agent that prioritizes safety.
Indeed. SARSA is guaranteed to converge to an optimal policy if all state action pairs are visited infinitely often and the exploration eventually diminishes, for instance, by slowly decreasing epsilon over time so the policy becomes more purely greedy.
Now, you mentioned another TD control method, Q-learning. How does that compare to SARSA? It sounds like they might have different philosophies.
They absolutely do. Q-learning, introduced by Chris Watkins in 1989, was a true breakthrough because it allowed an agent to learn the value of the optimal policy while following a different policy, often an exploratory one. This is what we call off-policy learning.
Off policy, so it can be exploring randomly, making mistakes, but still learn the best possible path as if it were always acting optimally. That sounds incredibly powerful, almost too good to be true.
It is remarkably powerful. Here's its algorithm. Q is Saint, West Alpha RT plus 1 plus Gamma Max QST plus 1.
Okay, wait. The difference from SARSA is subtle but critical. Instead of using QST plus 1, the value of the action actually taken in the next state, like SARSA does. Q-learning uses QST plus 1n, which represents the value of the best possible action in the next state.
Bingo.
It's always picking the best future regardless of what it actually chose to do next.
Exactly. This is the core distinction and the essence of off-policy learning. Q-learning optimistically assumes the best possible future. It's effectively saying, even if I, the agent's current behavior policy, take a random step now, I'm going to update my knowledge of the current state action pair based on what the optimal path would be from the next state, assuming I could take the best action there. This is why it's off policy. The values it learns are for toward dollars, the optimal action value function, directly. The policy being followed doesn't contaminate the values being learned.
So it's learning the ideal strategy, even if its current actions are a bit messy due to exploration. Let's really hammer this home with the classic cliff walking example from our sources. This sounds like it will illustrate the difference perfectly.
It's the perfect illustration. Imagine a grid world where you must navigate from S, start, to G, goal. Directly below the safe path is a cliff that, if entered, gives a huge negative reward and forces you back to the start.
Okay, avoid the cliff.
SARSA, on policy, because its updates factor in its own exploratory steps, tends to learn a slightly longer, safer path that stays away from the very edge of the cliff.
Because it might accidentally step off during exploration.
Right. If an exploratory step causes it to fall off, that negative reward influences its Strondel values for the actions that led to that fall, making those actions seem less desirable, thus leading to a cautious optimal path.
Okay, and Q-learning.
Q-learning, off policy on the other hand, will learn the shortest possible path, even if that path skims the very edge of the cliff.
Really? Why?
Because its updates always consider the maximum future value, effectively ignoring the negative impact of its own exploratory falls when calculating the optimal path. It doesn't penalize the optimal policy for the behavior policy's exploratory mistakes. It always aims for the ideal, even if its current self is still learning and making errors.
Wow, that's a profound difference in outcome. Q-learning is more aggressive in finding the absolute shortest path because it divorces the learning of the optimal policy from the potentially suboptimal exploratory policy used for gathering experience. It seeks pure optimality.
It's proven to converge to the optimal action value function under certain conditions, primarily that all state action pairs are visited infinitely often, ensuring enough data is collected.
Before we move on to how we can look even further ahead, you mentioned something called afterstates. How do they fit into the picture of learning actions more efficiently?
Ah, yes. After states are a brilliant optimization for certain types of tasks, especially those where the immediate effect of your action is completely known and deterministic, but the subsequent environment response is unknown or stochastic.
Like in games.
Exactly. Classic examples include games like tic-tac-toe or backgammon. Instead of learning a value function over state action pairs, which can be numerous, we learn it over after states.
Okay, what's an afterstate again?
An after state is the state after the agent has made its deterministic move, but before the environment's unknown response. For example, an opponent's move or a dice roll.
So in tic-tac-toe, if I place an X in a square, the resulting board configuration before my opponent moves is the afterstate.
Exactly. The efficiency comes from the fact that many different state action pairs can actually lead to the same after state. For instance, putting an X in the center square might be the best move from several different initial board configurations.
Right.
By learning the value of these after states, knowledge gained from one particular move immediately transfers to all other moves that result in the same after state. This can significantly speed up learning by reducing the number of unique situations for which you need to estimate values, making the problem space smaller and more manageable.
That's a really neat trick for efficiency, especially in complex games.
It really is. TD Gammon used this to great effect.
So far, we've focused on one-step TD methods like SARSA and Q learning, which update after every single time step based on the very next observed reward and estimated next state value. But what if we want to look a little further ahead than just one step, yet not necessarily all the way to the end of an episode like Monte Carlo? Is there a middle ground for our learning?
That's an insightful question, and it leads us directly into a powerful generalization: in-step TD prediction. This concept truly explores the entire spectrum between pure Monte Carlo, which looks all the way to the end of an episode.
Waits for the final score.
Right. And one-step TDO, which looks only one step ahead. It allows us to fine-tune how much actual experience we gather versus how much we bootstrap from our estimates.
How do we construct these end-step returns? What do they actually look like in terms of rewards and value estimates?
We construct intermediate targets that look ahead n steps into the future. A one-step return is what we've already seen with TD0, RT plus 1 plus gamma VST plus 1. You get one immediate reward, and then you bootstrap from the estimated value of the state one step ahead.
Okay, familiar.
A two-step return would look further. Dorfe 2 plus 1 plus gamma RT plus 2 plus gamma 2 VST plus 2. Here you get two actual rewards, and then you bootstrap from the estimated value of the state two steps into the future.
So more real rewards, less reliance on the immediate next estimate.
Exactly. An n-step return generalizes this. Goral T plus 1 plus gamma RT plus das plus gamma nun 1 plus gamma phi plus blotties theta st. You collect n actual rewards and then bootstrap from the estimated value of the state n steps into the future. And of course, an infinite step return, or our return until termination, is simply the full G2, which is the target used by Monte Carlo methods.
So n-step TD methods update state values by aiming towards these n-step returns. They are still fundamentally TD methods because they use a bootstrapped estimate, gamma or their VS, for the remainder of the return after no actual rewards have been collected.
Exactly. The real beauty here is that often an intermediate value of n, neither one pure one-step TD nor infinity, pure Monte Carlo, yields the best performance.
A sweet spot.
Sweet spot. It perfectly balances two important factors: the bias of short-term bootstrapping, which relies heavily on potentially inaccurate early estimates, with the high variance of long-term Monte Carlo returns, which can be noisy because they sum many random rewards over a long period.
Less bias than TDDU, less variance than MC. Can you give us an example where this sweet spot of an intermediate din really shines and helps learning?
Consider the classic random walk task. This is a very simple task where an agent moves left or right along a line, eventually terminating at one end with a reward. Empirical studies for such tasks consistently show that n-step TD methods with an intermediate n, say 1n44 or 180, often achieve lower error and converge much faster than either one-step PD, TD0, or pure Monte Carlo, which is effectively infinite n.
Interesting.
This finding is critical because it highlights the power of extending TD beyond just one step, showing that carefully balancing actual experience with bootstrapping is often the most efficient way to learn.
That's fascinating, finding a sweet spot and how far to look ahead. But what if we don't want to just pick a single n? What if we could somehow combine all these n-step returns, giving more weight to some and less to others, in a truly intelligent way?
That's where the truly elegant and powerful concept of eligibility traces, particularly embodied in the TD algorithm, comes into play. The core idea is to combine all n-step returns into a single comprehensive target, weighting them appropriately.
So it's not just one in n that we pick, but a clever blend of all of them. How does that weighting work?
Yes, precisely. The lambda return is a weighted average of all n-step returns. The weight given to an n-step return decays exponentially with n, and this decay is governed by the parameter lambda, where it's 0 lambda lambda.
Okay.
This parameter allows us to smoothly interpolate between TD0 and Monte Carlo.
How does that lambda parameter control that interpolation?
It's quite intuitive if lambda error return effectively collapses to only consider the one-step return. This means TD lambda becomes exactly equivalent to TD0. It's only looking one step ahead.
Pure TD0.
If lambda rare-will wall return collapses to include the full Monte Carlo return, giving equal effective weight to all steps up determination. This means TB lambda becomes equivalent to a constant alpha Monte Carlo method. It's looking all the way to the end of the episode.
Pure Monte Carlo.
Yeah.
So lambda is a powerful knob that lets us dial in how much of a short-term immediate feedback view, like PD0, or a long-term full episode view, like Monte Carlo, we want our agent to take. But how does this elegant combination actually work mechanically in real time? That sounds like it would require looking into the future.
You're right, the concept of looking into the future to calculate the lambda return is called the forward view. It's theoretically elegant, defining the optimal target, but it's not directly implementable in real time because, as you said, it needs future information.
Can't predict the future.
Not easily. This is where the backward view comes in. It's the mechanistic and practical way we implement TD0 incrementally, step by step. This is where eligibility traces become the core mechanism.
Eligibility traces. That sounds like a sophisticated memory system for important states.
That's a perfect way to think about it. An eligibility trace, or ES, is a temporary numerical record that remembers which states or state action pairs have been visited and, critically, how recently they were visited.
A memory trace.
Think of it as a rapidly decaying memory or a credit counter. A common type is accumulating traces. When a state stall is visited, its trace at 0 is incremented by 1. Then, at every subsequent time step, all traces for all states that were previously visited decay by a factor of gamma lambda.
So they fade over time.
They fade. For the current state, its trace updates as it's a ET1 plus theta, while for any other state that wasn't just visited, its trace simply decays. It's LT AAT, AT hun, ETC DT1.
So the trace for a state spikes up when you visit it and then slowly fades over time like an echo, unless you visit it again, which re-energizes its trace.
Exactly. The genius of the backward view is how it uses this trace. At each step, the current TD error is calculated, just like in TDO, but then this error isn't just used to update the current state. No. Instead, this error is broadcasted backward in time to update the values of all previously visited states, with the amount of update being proportional to their eligibility traces. The update rule for the value of any state then becomes liver V's plus alpha delta ES.
Wow, so the surprise gets sent back to all the states that led up to it, based on how strong their memory trace is.
Precisely. It provides a causal, incremental way to approximate that theoretical forward view. It efficiently spreads the credit, or blame, for a reward or TD error back through all the states that led to it, with more recent and more frequently visited states getting more credit.
This sounds incredibly intuitive. It's attributing good or bad outcomes to the entire sequence of events that led up to them, with more recent events or those that had a stronger echo in memory getting more significant blame or praise.
It is remarkably elegant. Consider the grid world with reward example from figure 7.13 in our sources. If an agent takes a specific path that eventually leads to a high reward state, a one-step SARSA agent would only strengthen the value of the last action taken immediately before receiving that reward.
Just the very last step gets the credit.
Right. But a SARSA agent would intelligently strengthen the values of many actions along the entire path that led to that reward. The strengthening effect would gradually decay, for example, by a factor of gamma lambda equals 0.99 cents per step as you go further back in time.
So the whole path gets reinforced, but the steps closer to the reward get more credit.
Exactly. This makes learning much faster and more efficient as the good or bad consequence is attributed to all relevant preceding actions, not just the final one.
That dramatically speeds up learning, especially in tasks where rewards are sparse or significantly delayed, which is a common problem in real-world applications.
Huge difference. #4.3 SARSAs and Q lambda with eligibility traces.
The powerful concept of eligibility traces extends very naturally to action value functions,
Hmm.
which is crucial for control problems. How does that work for SARSA?
Right. For Sarsalanda, we use eligibility traces for state action pairs. The trace for the current pair is incremented, and all other traces for previously visited state action pairs decay. The TD error still uses 2q plus 1 at plus 1 because it remains an on-policy method.
Sticking to the actual path taken.
Yes. The update is QSA left arrow Q plus A plus alpha delta. This makes SARSA converge much faster by assigning credit over longer sequences of actions while still learning the value of its current potentially exploratory policy.
And how about Q learning with eligibility traces? Can we combine that off-policy learning power with the efficiency of traces?
That brings us to Watkins's Q. It's a variation of Q learning that does indeed incorporate eligibility traces. However, there's a crucial and very interesting detail. The eligibility traces are immediately set to 0. They are cut off whenever an exploratory, non-greedy action is taken.
Cutoff. Why the immediate cutoff? That seems to defeat some of the purpose of traces, which is to spread credit back over time.
It's because Q learning is trying to learn the optimal policy, irrespective of its current exploratory behavior. If the agent takes an action that is not the best according to its current QDAW values, i.e. an exploratory action, then that part of the path is considered off track for the optimal policy.
Ah, okay.
So the credit assignment for optimal learning is reset. Any state action pairs visited before that exploratory action are no longer considered relevant for the current update towards the optimal policy because that path diverged from the optimal one.
That makes sense in theory for trying to learn a pure optimal path. But what's the practical implication for learning efficiency, especially if the agent is exploring a lot?
The limitation is exactly that. This trace cutoff can significantly reduce the advantage of eligibility traces if exploration is frequent, which it often is, especially early in learning.
Right.
If you're constantly cutting off traces, then only rarely will backups of more than 1 or 2 steps actually be performed. In such scenarios, learning might not be much faster than plain one-step Q learning. It's a trade-off between the theoretical purity of learning dollars and the practical speed-up provided by long traces.
So, while conceptually sound for off-policy learning, frequent exploration can undermine the efficiency benefits of eligibility traces in Q. That's a fascinating design choice.
It truly is. Beyond accumulating traces, by the way, there are also replacing traces, where a trace is set to 1 instead of incremented when visited, and Dutch traces, which cleverly combine elements of both. Each has slightly different properties and can be more effective in specific scenarios, especially when we start combining these ideas with powerful tools like function approximation.
Always more layers to peel back.
Oh.
We've built up this incredible toolkit of learning methods, from the basic TD0 to the sophistication of SARSA lambda and Q lambda. But in the real world, problems often involve enormous, even continuous state spaces. We can't just have a giant table to store a separate value for every single state or state action pair like our tabular methods assume. So how do we actually apply these brilliant ideas to massive problems?
You've hit on a critical point that takes RL from theory to real-world impact. Function approximation becomes absolutely essential. For many real-world problems, think about controlling a robot with continuous position and velocity, or playing games like backgammon with an astronomical number of discrete board positions, far too many for a table. It's simply impossible to store a separate value for every single state or state action pair in a table.
The table would be too big or infinitely big for continuous states.
Exactly. So we need a way for the agent to generalize its learning from the states it has seen to the states it hasn't seen, or to states that are very similar. The solution is to represent the value function with a parameterized function. Instead of individual table entries, we use a function like a neural network, a linear function, or even simpler techniques like tile coding, where a small vector of weights defines the entire function.
So a smaller set of knobs, the weights, control the value estimates for everything.
That's the idea. The magic here is that changing one weight can affect the estimated value of many states simultaneously, allowing for powerful generalization.
And how do we actually adjust these weights during learning? Is it still based on the TD error?
Absolutely. Gradient descent methods are commonly used for this. They iteratively adjust the weights in the direction that minimizes the error in our value predictions. Critically, TD SARSA and Q lambda can all be combined with gradient descent function approximation.
How does the update work then?
The update for our weights typically becomes dt plus 1 plus alpha delta AR dollar. Here, the R vector of weights, alpha is the step size, delta is the TD error we've been discussing. And out dollars is now a vector of eligibility traces, one for each weight. These eligibility traces are derived from the gradient of the value function with respect to the weights, effectively telling us how responsible each weight was for the prediction in the visited states.
So the traces are now tracking the eligibility of each weight in the network to be updated based on its influence on recent predictions,
Yeah.
rather than just individual states. That's a clever extension for complex systems.
It allows the learning to generalize efficiently across similar states, making these methods applicable to vast problem spaces. Consider the mountain car task from our sources.
Ah, yes, the little car stuck in the valley.
Right. This is a classic continuous control problem where an underpowered car is stuck in a valley. It needs to learn to swing back and forth to gain enough momentum to climb a steep hill to reach a goal at the top. This isn't a simple grid world.
Definitely not tabular.
No. SARSA combined with linear function approximation, specifically using tile coding to discretize the continuous position and velocity into overlapping features, successfully solves this problem, demonstrating its power in continuous spaces.
How does an agent explore effectively in such a continuous and potentially vast space, especially when it doesn't even know what to do initially?
One clever technique often used, particularly in early learning stages, is optimistic initialization.
Optimistic.
Yeah. Instead of starting action values at 0, which might be typical, you set them to an unrealistically high value, e.g. 0, when all rewards in the environment are actually negative. This naturally encourages exploration,
How so?
because the agent is always disappointed by the observed rewards, which are much lower than its overly optimistic initial estimates. This constantly drives the agent to try new things and explore new states, pushing it away from wherever it has been until it finds a genuine solution.
Huh. That's clever. It's like it starts out thinking everything is amazing, gets disappointed, and keeps searching for something that actually is amazing.
Exactly. It's a neat alternative or complement to relying solely on epsilon greedy for exploration.
That's brilliant. It's effectively baking exploration into the initial value estimates themselves, creating a built-in drive to discover better outcomes. Now, let's talk about a famous real-world success story that brought many of these ideas together in a groundbreaking way. TD Gammon.
Ah, TD Gammon. Developed by Gerald Tesoro at IBM in the 1990s, this was a truly monumental program. It learned to play backgammon at a grandmaster level solely through self-play and reinforcement learning.
Solely through self-play. No human games fed into it.
Nope. This was a massive accomplishment at the time.
That's an incredible feat for a game as complex and nuanced as backgammon. How did it achieve this without being explicitly taught by human experts?
TD Gammon leveraged exactly the ideas we've been discussing. It used the TD lambda algorithm, specifically with lambda on.
So like the Monte Carlo end of the spectrum for credit assignment.
Pretty much, yeah, in terms of looking back over the whole game. But critically, it still performed continuous updates after every move, which is very TD. It employed a multi-layer neural network for function approximation because, as we touched on, the number of possible backgammon board positions is astronomically large. Far more states than could ever fit into a simple lookup table.
Needed that generalization power.
Absolutely. And it learned an after-state value function, taking advantage of the fact that the immediate outcomes of dice rolls and moves are deterministic.
So it smartly used after states to reduce the complexity and the learning process. Was it like the agent just played against itself?
Precisely. The most impactful part was its learning process. It played millions of games against itself, starting with entirely random weights in its neural network.
Millions, starting from random.
Millions. Initially, its moves were awful, essentially random. But gradually, game after game, by observing the outcomes of its self-play and using the TD updates to adjust its neural network's weights, it improved rapidly. It continuously refined its understanding of which board positions were good and which actions were best in those positions.
So it literally taught itself to play grandmaster-level backgammon without any human instruction or pre-programmed game knowledge. That's the ultimate trial-and-error success story.
It absolutely is. The impact of TD Gammon was enormous. Unlike previous strong backgammon programs, which relied heavily on extensive human-crafted domain knowledge or explicit expert examples, TD Gammon demonstrated the incredible emergent power of TD learning to discover complex strategies from raw experience.
Wow.
It foreshadowed many of the AI breakthroughs we see today, from game-playing AI to complex control systems, all built upon these very foundations.
A real landmark achievement.
Truly. Hashtag tag tag outro.
What an incredible journey we've been on today. We started with the fundamental idea of an intelligent agent interacting with an environment, driven by the goal of maximizing cumulative reward.
Right, the core RL setup.
We saw how Monte Carlo learns from complete experiences requiring patience and how dynamic programming can find optimal solutions, but demands a full model of the world and struggles with scale.
The two foundational extremes, in a way.
And then we witnessed the elegant fusion of these ideas in temporal difference learning, or TD learning. This breakthrough enabled agents to learn step by step from partial experience without needing a full model of the environment.
Yeah, that ability to update after every time step rather than waiting for an entire episode to conclude is a core innovation that completely changed the game, model-free and bootstrapping.
We then dove into the practical, action-oriented applications of TD learning. Sarsa showed us an on-policy approach, where the agent learns the value of the policy it's actually following, including its own exploration leading to cautious, safer paths.
Learning from its actual experience, mistakes and all.
Then came Q learning, the off-policy breakthrough, which allowed an agent to learn the optimal policy directly, regardless of the exploratory actions it takes, driving it towards the absolute best path, even if it's risky.
Aiming for the theoretical best, separated from the messy reality of exploration, a really powerful idea.
And by introducing end-step bootstrapping, we saw how to find a sweet spot in learning, looking ahead more than one step, but less than a full episode. This culminated in the brilliance of eligibility traces.
Right, which intelligently combine all end-step returns. These traces act like a memory, efficiently distributing credit for outcomes across entire sequences of actions, dramatically speeding up learning.
That backward spread of credit.
Exactly. Especially when combined with powerful tools like function approximation, as demonstrated by the groundbreaking TD Gammon.
From a baby gazelle learning to run, to a car learning to climb a mountain, to mastering complex games like backgammon, these methods are not just theoretical constructs. They are the bedrock of adaptive intelligence, constantly improving and finding solutions that even human experts might overlook.
Yeah, they empower machines to learn from experience in a way that feels incredibly natural, almost biological in some sense.
And here's a provocative thought for you to carry away from this deep dive. Think about a skill you've learned, anything from riding a bike to mastering a new craft. Was it purely through explicit step-by-step instruction, like supervised learning? Or did you learn by trying things out, experiencing consequences, positive or negative, and making adjustments for future attempts, even if the aha moment or the full reward came much later?
That trial and error, the feeling your way forward?
Exactly. How much of human learning, both conscious and unconscious, resembles these principles of reinforcement learning and temporal difference credit assignment? Perhaps understanding these algorithms gives us not just a glimpse into the future of AI, but also a deeper insight into the very nature of learning itself.
Something to chew on, definitely. A fascinating connection.